I really appreciate this invitation to give this presentation on open access GNSS datasets for investigations of extensional settings. This is a presentation based on a paper written in co-authorship with Corney Kramer at University of Nevada, Reno. A lot of the data that I'll discuss has been funded for collection by the National Science Foundation, as well as National Geographic, and much of it is stored at the EarthScope Consortium. So I'd like to give credit to those institutions as well. So my talk today will have 5 parts. I'll give you a little bit of motivation behind this presentation, talk about precise position estimates, time series analysis, and parameter estimation, applications for extensional settings, and resources at the end. So as I mentioned, this work is related to a paper published in 2024 called Open Access GNSS Data for Studies of the Lithosphere. And today I'll focus more on applications to extensional settings. This is an open access publication, so anyone should be able to access it and download it and read this manuscript. We go through the purpose of using GNSS data for investigating lithospheric studies, so particularly rheological properties of the lithosphere, as well as dynamic processes that can deform the lithosphere. In this lovely figure shown here, which is actually modified from a figure published by Elliott et al. In 2016, he kindly sent us the figures that we could modify it and extend it down to the top of the asthenosphere, and then make it so that it has nice little GNSS instruments on the top and has a GNSS satellite. But it shows an example part of the lithosphere. This is actually a strike slip setting. So this image helps to illustrate parts of the lithosphere that can be investigated with studies or observations of surface motions with GNSS at the surface here. And we have this satellite that's propagating signals down that are being collected by these GNSS stations on the surface. And then over to the right, we have a generic strength profile illustrating the rheology of an example rheology of the crust and upper mantle, which is also possible to investigate with GNSS observations. In order to obtain those GNSS observations, we need some nice instrumentation at the surface. These are some examples around the world. A, B, C, these are all continuous GNSS instruments. So they stay there in their locations permanently and are collecting data on a continuous basis. And then D, E, and F are examples of campaign instrumentation, also known as episodic GNSS. So these are sites that are set up on a temporary basis, usually for at least 72 hours, to gather enough data so that you can get a millimeter precision position. So speaking of those millimeter precision positions, let me go into how we obtain those. From the GNSS satellites, there are signals sent from those satellites. Particularly, you can use pseudo-range signals, Doppler signals, or the carrier phase signal. In particular, the carrier phase is the only one that can actually be used to derive millimeter precision positions. I have down here at the bottom what's known as the GNSS equation, or formerly the GPS equation, prior to multiple global navigation satellite systems orbiting the Earth. This one is simplified and available in this publication here. So the different terms, this is the carrier phase observation. S stands for satellite and R stands for receiver. So S is where the signal is deriving, and then R is where the signal is being received. Pseudo range is the geometric distance between the satellite and the receiver. Clock deviations have to be corrected for because the time at the satellite is different from the time at the receiver. The There's propagation errors, so the signal travels through the troposphere as well as the ionosphere. So those have to be corrected for. Phase ambiguity term. This is associated with when the receiver loses lock with the satellite signal itself, because satellites will um, pass over trees or pass over the horizon, and they'll lose lock with the instrument on the ground. And then there's this term at the end for additional errors. So in order to solve this equation to get millimeter precision positions, there's really two main processing techniques. One is called precise point positioning, or PPP. This one is pretty commonly used, but it is slightly less precise than differential carrier phase positioning, which is also known as network positioning. So B here, this was the original style of processing that was developed prior to these global networks of really high precision stations around the world. Precise point positioning leverages like the International Geodetic System. So it leverages these nice global networks of continuous stations, and you really only need one station, usually a continuous station, to calculate a position. The differential carrier phase or network positioning approach requires reference stations near your system of stations. And it is slightly more precise, but it does require more computational power. Precise point positioning, there's a number of software available to do that, such as Gypsy X. Network positioning, the software, some examples are Bernice and Gamma Globe K. So once you have the precise positions, you can produce time series. Over to the left is an example time series. We have a year along the x-axis, and then three components of motion. So east-west on the top, north-south in the middle, and up-down at the bottom. When we have, typically it's one position per day. So here, each blue circle is one position. So in A here, I'm showing you that this is the initial position and slope part of the equation that we use for modeling time series. So this is the initial position, and then this slope represents the velocity at that site. B, this is a coseismic offset. It's a Heaviside step function. Sometimes we need these if there are equipment changes as well. C is represented in the up-down component. There's often seasonal signals or hydrologic loading signals that should be modeled. This is a periodic function. It can have one or two components, so the annual and or semi-annual signal. And then the last part of this equation is a decay function for post-seismic decay. So in D, it's this part and this part here. It could also, so here it's written as an exponential function, but it could also be logarithmic or sometimes polynomial, depending on how a person wants to model that. Okay, so let's talk about some applications of using this data. So the secular velocities, so these are the long-term velocities, they're linear, they don't really change over millions of years. These can be used to study plate motions, and I have an example from a recent paper by Kwagalakwe et al. 2025, where she constrained the Victoria microplate motion at this new, she found a new Euler pole up here at 1 using newly available and like the most robust velocity solution for the area. One can also use secular velocities to study deformation zones, whether or not a plate interior is stable. In East Africa, for example, there's a part of the Victoria microplate where the North Tanzania divergence is breaking into the Tanzania craton. So one could use GNSS to study that area. GNSS velocities can be used to study geodetic strain rates. And then they're very useful for comparing with predictions from geodynamic models as well. So these secular velocities. Post-seismic decay, so this would be derived from the time series. These are great for studying afterslip processes, poroelastic effects, rheological properties of the lithosphere. On the right, I have a map of a predicted post-seismic signal in Southern California from Guns and Bennett 2020. I just found this one was a nice example of being able to pull out a potential post-seismic signal from GNSS velocities. But if we had a large earthquake occur in an extensional setting where we had GNSS velocities, one could also study any of these processes, provided that the signal is large enough to capture. Some other examples, so one could look at the periodic signals. Um, so uh, signals coming from the hydrosphere, such as oceans and lakes, signals coming from atmospheric processes. If there was a rift in a setting where there was ice, the cryosphere, soil moisture, so things, processes happening in the critical zone can be captured. And the figure to the right, this is a study by Zhu et al. 2021. Um, Again, not in a rift setting, but a good example of the top is time series, so years along the x-axis, and um, different signals that were captured in the data and then modeled below in displacement. So they were able to find signals of lake storage, snow, soil moisture, and then the background signal. Co-seismic offsets. This is an example on the right from the Natron Rift and the East African Rift System. The red vector is a GNSS velocity. It was a co-seismic offset, and this information combined with INSAR data and some Coulomb stress change modeling was able to really advance the understanding that slow slip and aseismic slip was important for accommodating strain during extensional events. So understanding the science of fault mechanics and then the release of strain during an earthquake is another application. So some other examples, dynamic topography. So as we get more and more precise observations, understanding the effect of plumes, for example, which can be quite important in rift settings. And then resolving subsurface magmatic plumbing structures can be resolved as well. This on the right is an example from Dowd et al. 2024, where he inverted data from Old Yanyulingai in Tanzania to constrain an approximately 3 kilometer depth magma source relative to the peak of the volcano itself. So I think I'm getting close to time, so I'll get to resources. So in the paper, you can find all of these links as well, but we provided several resources for finding available time series from NASA, the NSF Gauge facility operated by Earthscope, also in the Nevada Geodetic Laboratory provides them for secular velocities and potentially velocities that have other signals as well. There's the Gauge facility, NASA, the Nevada Geodetic Laboratory, and an organization in France. For some derived products like strain rates, also the Gauge facility, Nevada Geodetic Laboratory, and NASA. So finally, we provided 34 repository links in the paper if somebody wanted to access RINEX files and process their own data. And this is just a snapshot from the paper of 7 of the repositories. So I'm pretty sure I'm at time, so I will stop here.
Thank you, Sarah. That was great. That's exactly the kind of material I'll be using in class. So thank you very much for that. Are there any questions? I see the participants list. So if you have a question, please put your hand up, or you can put your information in the chat. A quick question, and this is not my field, so I apologize if it's dumb. In terms of the precision that we're now achieving with the modern networks, is there kind of a timeline beyond which things get a bit too sketchy, and we really want to limit ourselves to certain years worth of data for highest accuracy?
Um, that's a good point because prior to certain time periods, like let's say the early days of the global positioning system, like the 80s, there weren't a lot of observations. We didn't have the robust global networks. I don't know that I would say there's sketchy observations. It's just that you're going to have larger uncertainties probably as you go further back. Like if you're looking at data from the 90s and maybe early 2000s, you would have larger uncertainties. It's not so much that I think the precision is wrong. It's just, it's maybe not going to be as tightly constrained, if that makes sense.
Cool. So like the last 15, 20 years should be fine.
Should be pretty good. Yeah. And note that you're not going to always get the same result as far as like the exact uncertainty ellipse from every solution or the exact vector from every solution because of the different processing techniques. Um, but as far as like, are you at the right place on Earth? That's pretty well, like we've gotten that
Understood.
down pretty well. Yeah.
Okay.
Sasha.
Sasha, you have your hand up.
Yes, right. Thanks. Great talk, Sarah. You have a lot of experience in putting GPS stations in East Africa, building collaborations, maintaining these stations. What is your view on the future of the network in East Africa in particular? Which kind of region do you think would be most valuable to get new stations in, and how would that be possible in the longer run?
Thank you for that question. I think stations everywhere is the future. There's still so many gaps in not only East Africa, but many other parts of the African continent. Um, I mean, I can speak from my own experience of trying to build out networks from projects. So I've been trying to build up in Uganda because that's where I've had some success and continuing to build that out and then work with the Ugandan government to build it into their budget to maintain those stations long term. So that's still an ongoing active process. As far as continuing to fund stations and keep those stations going, the Africa Array community is being revitalized. So that was an effort that lasted over like 30 years, but lost its funding from the NSF, from the US side. But it's starting to get revitalized. So we're having our first Africa Array meeting in South Africa in January, and so that's we're bringing like 15 to 20 delegates across the continent together to discuss really the future of seismic and geodetic data in across the continent. So hopefully that will lead to some good discussions and ideas. But as far as places, yeah, I think my answer to that is like everywhere that it's possible, because um, yeah, having better constraints on positions all over the world is valuable, to many different fields.